anymore, so I don't know if you're watching it or not. But hopefully you're able to muddle through some of this. But if not, that's what I'm here for. That's why I wanted to come in today. I thought I could make up a bunch of videos. Oh, and just so you know, my wife's doing great. She's at home napping now. I've got a babysitter for her. At least that's what I say. So I had a babysitter yesterday, came to campus and dealt with a few issues. And then today I got a babysitter. The babysitter is my mother-in-law. And she does not like having that babysitter. I got to be honest with you. So she'll be thrilled when I get home this afternoon. But I'm glad that she has someone with her, and she is recovering as expected, whatever that is supposed to mean, I guess. So yeah, nothing bad. So we've been thankful, and thank you for those who were praying. But anyway, let's take a look at this and see if you have any issues or questions with the secant method and Newton's method. There was only one, is that right? One question on secant, if I remember correctly. There might be some more on Newton's method. Let me grab it here so that we know what we're talking about here. We're doing root finding methods and specifically Newton's method. And the secant method was kind of embedded inside this. There was some information about that. So here we have the exercises. Okay, yeah, let's make it a little bigger, right? And it's still small. Isn't there a way to make this bigger? There's the view. The sec menu. This would probably help me if I looked at this screen. Is there like a view? Oh, here, view. View, page, zoom, fit to width. There we go. That's what I wanted. Okay, so is this what you did? Yeah, I forget which problems you had, but I'm happy to talk about them if need be. So, yeah, so what sorts of issues do you have, if any? You understand? Like, let's do Newton first, and then we can touch on secant. Secant is just like Newton, but if you don't know the derivative of the function. So is there anything that we need to help? It was that easy. Well, that's encouraging. Or you didn't do it. It's okay. Wait, does it say you had to do it for today or for Monday? For today? Okay. I couldn't remember. I think, yeah, I couldn't remember if I said do it for today or for Monday, but whatever. Yeah, I was in the hospital making videos for everybody, and I'm like, oh, it says Monday. It says Monday. Okay, well, there you go. Maybe you don't have any because you didn't do it, and you were honest about it because, you know, it's due Monday. Yeah, so I think I was thinking on Wednesday, I didn't think I'd be here. So I thought, well, I'll just have it due Monday, and we'll pick up the pieces then. Okay, well, if just pause for a minute, make sure. Okay, you'll get more of this actually today, because today what we're doing is we're doing what are called bracketing methods, and bracketing methods solves one of the issues that you have with both of these methods. Let me just remind you what the issue is that you have when you're doing Newton's method. So here's the, where is it? There it is. Nope, that's not it. There it is. Okay, so the issue with Newton's method and the secant method, for that matter, is that you could end up not finding a root because either there's some sort of asymptotic behavior of the function, or there might be some sort of a weird hump somewhere near the x-axis. Just to give you, I know I did this probably on the video that I did for you from the hospital, but like if you have something like this, that function, and you're looking for the root, if your guess, so if your guess is over here somewhere, then you're going to be in good shape, right? Because the method is you find the tangent line and you follow that tangent line until it crosses the x-axis. That's my new guess. And then that's going to be here. And then, of course, you can kind of see that this is going to converge pretty quickly, probably to this point here. But if, on the other hand, you accidentally pick a point over here as your first guess, and if you don't know the shape of the function, you know, you just pick a number and then hope for the best. I mean, you should try to educate yourself first, of course, but or maybe even over here. You might say, oh, that's so close. It's so close to the x-axis. Might be near a root. Well, anyway, for this one, you go like this, and then you're like, oh, there's my new guess. And then you go like this. Sorry, that's more of a secant line. And here we go. And then here's the new guess. And that just sends you off to infinity. So if you have an asymptote either y equals 0 asymptote or some other asymptote, it's going to fail. So these are fails. So how can we guarantee that this is not going to fail? That's the big question. Because Newton's method is super quick. So the difference is that bisection method is you get a linear convergence. Newton's method is quadratic. So it's not just twice as fast. It's like you get twice as many digits each time you do an iteration generally. So we'll talk about convergence rates probably Monday. No, I think we'll do Python Monday and we'll talk about convergence rates on Wednesday. At any rate, that's just a general idea of Newton's method. So how do we bracket? Well, the idea behind bracketing is you take that method and you kind of combine it, do a hybrid of this method with the bisection method. So here's the Newton's bracketed method, bracketed Newton's method, I should say, and bracketed secant method is very similar. I'll show you that one as well. So those are the only two things we want to go over today. I just wanted to touch base, make sure everyone's okay. Yeah, I have to leave a little early to make sure I get to the meeting, but anyway, and so let's go over this and see what this means. I know that's a lot of words, but it makes more sense if you think of it in terms of an actual problem. So I'm going to just copy this so that I can copy this. There it is. So that I can write on it a little bit more easily, because the PowerPoint is not the best. Let's copy and delete. Now let's grab this. Nice. There we go. Okay. So we're going to start off, and unlike Newton's method, you're going to choose two guesses. So this is going to, like I said, it's like a hybrid between Newton's method and the bisection method. So we're going to choose two guesses for for where the root is. There we are. So let's just put an example here, and I'm going to use as my example function this. Oh, what am I doing? Let me try again. This function that I gave you as an example of where Newton's method fails. So there's my example. That's what I'm going to use. And then what you're going to do is you're going to pick 2 points. And the important thing is that these 2 points should be similar to the 2 points you pick for the bisection method. So for this particular one, I'm going to just pick this point right here as x0 and this point right here as x1. Clearly, the function values are on opposite sides of the x-axis, and as long as this is continuous, we're guaranteed that this is going to go through the x-axis somewhere between those. So anyway, that's the start. We start off by coming up with, oh, I see an error. I typed this up this morning. Sorry, I cut and pasted a little too much. Let me just get rid of that. Yeah, I cut and pasted I typed up the secant method first, and then I cut and pasted and just modified it. But there. So we have x0 is our first guess, x1 is our second guess. And now what we're going to do is we're going to find the root of the tangent line that goes through x1. So let's go ahead and do that. Here's this. Right here this is the tangent line. There is the root. Now, you already know the end of the story here, don't you? Because we talked about this just a minute ago, that if we continue using this as our next guess and then do it again and again, we're going to go off, go off to Never Land, to infinity and beyond. And we don't want to do that. We want to get closer to the root. So this is no good. So this is where the bisection method comes in, and that is this, that if the x2, so this is x2, this one right here, root of the tangent line, that's x2. So that thing is outside the original interval. And so since it's outside the original interval, we're like, oh, I don't want to go out there. I want to get closer to the truth, not further from the truth. So if it's ever outside the interval, the original interval here, then we're just going to take the midpoint. So that's not going to become x2. Like, no. We're going to choose to use the midpoint. So here, x2 is the average. And that is going to give me a better estimate. So now hopefully you can see that the next step is that we're going to basically do this again do it like the bisection method. So now that we've got another estimate, no matter how we got it, and I'll show you one more iteration, once we have another estimate, you ask, is this on the same side as the, which endpoint do I replace? So like the bisection method, you say, okay, this one is positive, the function value rather is positive. And so that's the same as the function value for the old x1. And so my new x1 is going to be here. And my new x0, which is really the old x0, is going to be there. And then we just repeat the procedure. So we've got an x0 and an x1. Take one of them. It really doesn't matter which one. And you're going to do Newton's method. And I guess that this is not going to work out as well as I thought. Okay, I think we can all see what's going to happen at this next iteration. Can you see that this is going to send me off away from my interval? So that's no good. So we'll just bisect again, if you don't mind. So we know that we're just going to have to bisect, and then we'll just do one more after that. So this is the new x2. The new x2 is on the same side as the old x1, and so we get to do this again. So this will be x0. This will be x1. Are the colors? No, that's not a good color. Let's do this. x0, x1. Now we get to have fun with Newton's method. So now with this new one, finally Newton's method is going to help us out. Draw that line in, and you're like, okay, here is this. So that's the new x. That's x2. And notice that x2 is on the same side of the x-axis as x0 is. So my new bracketing will be, this is going to be let's see, change colors yet again. This will be the new x0. This will be the new x1. Now, I guess there's one thing that I left off of my list there, and that is that what happens at this stage? Because obviously, if I use x1 again, I'm going to end up with, sorry, if I use x1 again, I'll end up with that same point, and that's no good. So at this point, you use whatever your newest number is. So your newest estimate was this one. So I'll start my slope there. I'll go up here, and then I've got, it's somewhere over there. I don't know where it is. I think it'll be to the left of the actual root. So anyway, that's where you're going to get your next estimate. So you always keep that root in between the two brackets, and you keep doing this until you're close enough, in quotes. And that just means that from one iteration to the next, it doesn't change by much. Okay, so is that it? Yeah. Okay, so the only thing that I should mention, I guess, here is that I left off this, that when you repeat step 2, you use the newest x for Newton. So whichever side of your interval was the newer one. So before it was this one, that was my first new x, the x2, and then it was this one. But then the next one, the next newest one on the next iteration, it would be this one right here. So you always just use the newest one because that one would presumably be closest to the root. So this just makes it so that you're guaranteed that you're not going to go off somewhere else. You'll always get to a root. So it kind of combines both of the methods that we have used. So what do you think? Any questions? I've got a real example in just a minute. I know this is a fake example. All right, yeah, let's take a look. No, let's just mention. So you might think, it seems like Newton's method. If you understand that, then you should have no trouble understanding this bracketed secant method. It's basically the same, except for when you draw this, I'll just draw 1 or 2 iterations here. So you have this. Here's my curve. And I will put 2 example points there. Oh no, sorry. If I touch my hand the wrong way, it does stupid things. So there's that. Okay, so the red dot is going to be X, well, it'll be B0, I guess, because A and B, we'll use A and B for left and right. And then this will be A0 on the left. That's there. So we're happy that these are on different sides. The only difference between this and this is actually very similar to the bisection method. For this, you do a secant instead of, so I would do this. So instead of doing the bisection, I do a secant, and this becomes my new estimated point. That's on the same side of the x-axis there as the b, and so that's going to replace my b for this iteration. So this will be b1, this will now be a1, and then you do it all again. So I'm starting up there, I connect the 2 dots with a secant line, and that gives me another estimate, and then you repeat. So you keep doing this. You can see that the very next estimate is going to get us really close. If you can sort of eyeball this secant line here, it's going to be pretty close to the actual root. This one, it's called the bracketed secant method, but it's also sometimes called, I don't know if our book says it called, I think they still call it, but this is also called the false position method. So just another word or another phrase for this particular method. All right, let's take a peek at this in a real example. So I was looking at our Python. We're going to have to do the Python, I think on Monday would be best. So be ready, bring your computer, and you'll need to have a Google login credentials of some sort, because to use Google's Colab, it's real just a nice, you don't have to download anything, and don't have to sign up for anything other than something you probably already signed up for, and that's a Google account. But anyway, this isn't really necessary to do, but here's what I wanted to show you, is I've got this function. Now you can see from the function, so this is a quintic. So x to the 5th, the double star means exponent in Python speak. We'll go over this on Monday. But anyway, this is a quintic, and there's this theorem from modern algebra that says that there is no quintic formula. So you're familiar with the quadratic formula. There is a similar formula to solve cubics. So any cubic can be solved using this cubic formula. Same thing for quartics, and then quintics, that's 5th powers. No formula exists to solve this. So there's no way to solve this by a formula like the quadratic formula, but we can use numerical methods, of course, to solve this. So I've plotted this for you so that you can see. And actually, I made this particular, can I get rid of this stuff? Oh, I can, good. Anyway, you can probably tell that I made up this function so that it would be interesting, but also would have a root that I knew where the root was. Let me just plot this 4.5, just get a little bit further so you can see what this looks like. There we go. There, oh, that's so good, isn't it? So let me turn off my ringer, it's annoying me. It's been beeping. You know how it is, I don't know, maybe you don't. Like if you have something going on and everyone wants to text you, how's she doing? And how the text, the same thing over and over again. But anyway, so you can see here that, that this function, it does have one root, and I actually strategically put that one root at the point 3, just so that you would know where it was. But here's the function here. I wish I could, oh, I can. Let me see if I can get this diagram onto my iPad. Give me a sec. It'll take just a minute. And then I should have done it earlier. I just didn't think about it. Can I, just a sec, I just realized. If I do this, can I right click and save? Save it, yeah. Let me just save this and then I'll open it on my iPad. There we go, we'll just slap it here in numerical methods land. There we go. Untitled. It is the untitled image. Okay, give me a sec. I'm going to put it put it up here. See if it's there yet. Numerical methods. This spring. Refresh. Untitled. Nice. Oh, beautiful. Oh, no, that's not bad. Okay, let's open this in another app. Notability. Oh, it's beautiful. Okay, so we'll do this both on the computer and on here so that we can keep track of what's happening. What I was going to do is I'm going to start with, let's see, let's do bracketed, let's do the false position or the bracketed secant method first. So we'll have A0, and here this is B0. So notice that the function values, so here's how this is going to shake out, and we're going to program this. These methods are really easy to program. In fact, they are so easy to program that Google will try to help you out multiple times. I programmed them this morning actually on Google Colab, and every time I typed something, Google was like, I think you want to do this, and it would have 3 lines of code, and I'm like, yes, actually, that's exactly what I want. So you're going to have no trouble with the programming. So those of you who are, yeah, it's a little annoying to be honest, but that's the way it is. So I've got my A0 and my B0. Those are the 2 sides, 1.0 and 4.0. And then I'm going to have to come up with f of A0 and f of B0. So we're going to get those 2 things. And then the last bit is going to be this formula. Let's see, I've got it here. I'll put it up on the screen. The secant line formula. And this is just like the Newton's method formula, only you divide by, so you'll be using, some of you will be using this for Monday, some of you did it for today. You're going to, instead of dividing f of x by f prime of x, you divide f of x by the secant line, which is a divided difference. That would be down here, but then you reciprocate it and put it up here. I think I mentioned that in the video. So if you haven't watched those videos, you can enjoy them or skip them because the formula is so easy. So I'm going to put that down as x2. Let's see there. You'll see, I just wanted to have something here. X1 minus x0. Okay. Yeah, I didn't, yeah, you'll see it's really messy. Yeah, so this is f of x1 minus f of x0. So this is just an approximate slope. And then, so it's this, but it's the same formula. So let's go ahead and do this on Google. Where's Google? There it is. I need to be able to see it though. Hold on a sec. Okay, so just to make it easier on you, like I said, on Monday we will do this, but I thought I'll just go ahead and crank this out. So I've got my function, and I can compute. Here we go. I was just experimenting down here, so I can substitute numbers into the function. So what I want to do is I'm going to do this formula. Now, let's see. You know what I'm going to do? I am going to do this. Just a minute. I need a. Oh, don't look at yourself. Sorry. Yeah, ignore that. Pretend you didn't see that. It's probably a violation of something. Okay, I just needed to, because I needed that on the right instead of, or the left instead of the right. Okay, so I'm going to be typing this formula. I'll just, when I type, if I type it in once, then I think I'll be okay from there on. So, because I can just cut and paste. And so we'll call this, I don't know, y. I'll just call it y. Y is equal to, what I'm going to do is I'm going to substitute x for x1, or I guess this is A0. Sorry, I should have used the same stuff. So I guess over here, this x1 is equal to b, and x0 is equal to a. Just to be clear, I just, yeah. Okay, so I will type in A0. I guess A0 was negative 1. Okay, we'll do -1. Let's see what we get. And then, actually, we don't need that, do we? Well, we'll get it anyway. Here, I'll just print these. Print. hadn't thought through exactly how I do this, and it's kind of silly to be typing all this stuff. So we'll substitute that in, and then we'll do the same thing and substitute the other endpoint. So we'll start gathering our data, and then there, and let's do this. Very nice. Wow, negative 400. Seriously? That doesn't sound right. That can't be right. Hold on a minute. I'm looking right. Oh, 1, positive 1, not negative 1. Sorry. It's where Python put the y-axis in a weird, or it's weird the way that they put it. Sorry, my mouse is on the wrong screen now. Yeah, I guess my mind isn't straight, but yeah, so it looks like they put the y-axis at 2.5 for some, just to make it look whatever. Okay, so let's go ahead and do this. Control Enter. Okay, that's better. Negative 1.8. So negative 1.8 and so on. You've got all those digits, which we care about, but I'm just going to do it like this. And this is 0.09. I have that. Yeah, 0.09. And then we want to get x2. So we'll do that. So yeah, we're not going to do the derivative yet. So we're going to do print. So just have to do this once. So f dot, sorry, it's x1, that's going to be, can I see this? Sorry. There we go. Okay, so we're going to do x1, which is the second number, that's 4, plus, or is it minus? It's minus, yeah, I should know this. Minus, now we do this divided difference. So we do 1 minus 4 divided by, and then f dot subs. That's how you substitute a number into a function, at least with this particular thing. Let's see, x1. So that's going to be f of 1 minus f dot subs of, did you see it? It knew what I wanted to do. It's so irritating. Okay. And then I'm going to take that, close parentheses, and then multiply that times x, or f of x1. That's it. Okay, give me a sec. F dot subs of x at 4. Okay, I think I've got too many parentheses now. Let's see if this works. Oh, yeah. Oh, I don't know. 3.85? Does that seem reasonable? Let's find out. Yeah, I think that looks reasonable. So that's going to be, so we have 3.85. Okay, so let's just see what this means in terms of reasonableness. I think I'm starting to regret this particular function that I picked, because I wanted to have it just come almost touch, like right there. There's a minimum there, by the way, and now I regret putting this. So I invented this function, and it was dumb, because there, oh, well, that's not quite right, is it? Let's try again. Yeah, so my new point is going to be here. So this is actually going to take a little bit longer than I'd hoped. So let's just go use these two numbers, 2 and 3.5, so that it'll be a little bit more encouraging. So we start here and here, and our first, there it is. It'll be right there. That'll be the first guess. And so this is bracketed, one's positive, one's negative. And then when you do the secant, the new one will obviously, hopefully you can see that it'll be positive. And so this will be my new bracketing. But let's just do one. Since I've got all this stuff typed in, it shouldn't be too difficult to see this one iteration. Of course, you would do it on a hand calculator, at least for the weekend homework, which I have not yet put up, but I will. Okay, so first of all, let's get the function values at 2 and at 3.5. So good enough. Yeah, 2. What's that? No. Yeah, 2 and 3.5. Okay, so let's do 2 and 3.5. Now that I've got it all, I should have had it typed ahead of time. So there's the function values. As you would expect, the 3.5 is above the x-axis. It's a pretty good distance. almost to one above, and then the 2, which you can't see because it's behind the web window, is right here, at almost a little bit more than -4. Is that what it was? Yeah, -4.4. Very nice. So now we'll do this. So now it's going to be 4. Instead of 4, we're going to use x. This is going to be 3.5. And I'm going to change the 1 to 2 and the 4 to 3.5. So the 1 becomes 2. Give me a sec here. So since I've already got this, and you can see that we could easily just automate this. Where is it? Where is it? There it is. Oh, come on. So here we are. So 3.5. And then we'll hit enter. And there's my new value. Oh, come on. There it is, 3.26. So the new value, 3.26, right there, 3.26. And so then the next iteration would be using 2 and 3.26, which you can see there. So then the next step would be to use those two. And I won't do it on the computer, but you can see what's going to happen is that if I connect those 2 dots, I'm going to be pretty darn close. Wait a second. See if I go down here, can I? Yes. Yeah, I'm pretty close. So that green line, that really thin green line, you can see is pretty close to the actual root. Here's where it seems to intersect. So my next guess would be there. And then I'd keep going. And eventually, I think I'll end up bracketing this like this. This point will eventually move over so that you're really, the iterations will be close together. So any thoughts on this? Any questions about how this works? Are we happy? All right, well, I should have had you do the Python today. So let's take do I have a preview of the homework? I don't think I do. Yeah, so I'll have to add that homework then. I mean, that's basically it. And there's no issues with the homework. I guess we're going to be dealing with a lot of homework on Monday, possibly. Okay, that's fine. Well, if you don't want to, if you're fine, I'm happy to just pause here, and then we'll pick up the pieces on Monday. And that way, I just wanted to make sure I came in, touch base. And yeah, it's way early, 20 minutes, but I'm glad to have come in at least. So if you do have questions, I'm going to just update the homework because I didn't put it up there. But it's just a few problems like this. If you can do secant, if you can do Newton, you're going to be fine.